Hello, and thanks for joining me today for the latest in the Global Mapper webcast series. My name is David McKittrick, Senior Application Specialist here at Blue Marble Geographics. And today, as you can see on the slide in front of you, we're going to be taking a look at the terrain functionality in Global Mapper, specifically looking at some of the analysis capability that can be applied to a terrain layer. In recent presentations, we have talked a lot about LiDAR. Certainly from a development perspective, we're doing a lot of work with Global Mapper to fully utilize LiDAR and point cloud data formats. We often reference the terrain element of a LiDAR point cloud and the fact that LiDAR is a raw material for a lot of those analysis tools. So we thought today that we would take a more detailed look at some of those analysis capabilities. Once you have actually generated that terrain model, what can you do with it? So we'll be looking at things like contour generation, various analysis, including Watershed and Viewshed analysis. We'll also be exploring maybe some of the features of the application you may not be as familiar with, some of the slope analysis capabilities that are in Global Mapper. So this is a recorded session, obviously, so unfortunately we do not have the opportunity to interact directly with you. If you have questions about any of the elements of the presentation, or indeed anything that you have encountered with Global Mapper, feel free to email us. The email address is geohelp@bluemarblegeo.com. I will put that email address in the description on our YouTube channel right below this video presentation. I'll also show you a slide at the end of today that you'll have that address as well. So let's take a look at some of the themes or some of the topics we're going to be covering in today's presentation. Well, I think it's a good idea to very briefly talk about the creation of terrain data. We'll look at some of the raw materials. I referenced LiDAR, and we will take a very quick look at some LiDAR point cloud data and how that can be used for generating a surface. We'll also look at a simple XYZ or XYZ file as the raw material for generating that surface model. And we'll take a quick look at some of the online resources that are available. Obviously, that's not a creation function, but it's an access point where you can get some terrain data. So essentially, we'll begin by addressing the question, okay, where do I start? How do I get some data? And we'll take a look at those options. First, analysis function. We'll take a look at some very simple volumetric calculation capabilities in the application. Simply defining an area and determining the capacity or the volume. We'll take a look at a couple of variations on that theme, both depth and capacity, as well as actual volume of a pile. Related to that, we'll take a look at some more advanced functionality that allows you to determine or to generate a modified surface. We're going to flatten the terrain, and as a byproduct of that, we will also be able to determine the volumetric characteristics. Essentially, we'll be able to optimize the elevation at which the terrain level is going to be flattened to accommodate perhaps it's a building site or some sort of structure that's being placed there. So this is a very, very powerful component of the application. Again, volume calculation as well as terrain modeling. Contour generation is probably the most straightforward and indeed one of the most commonly used components of the terrain analysis functionality in Global Mapper. We know there's quite a few users that have Global Mapper in their back pocket specifically for this purpose, the simplicity of generating vector contour lines and if required, ultimately exporting them for use in a third-party application. Very straightforward process, but once again we'll take a look at some of the variations on the theme of contour generation. Line of sight and viewshed analysis, two variations on the idea of determining visibility along either a linear path or in multiple directions. We tend to think of these in the context of broadcast technology. If a radio transmission would be beamed in a certain direction, can that signal be picked up, or what's the coverage area for that signal? But there are other applications for this as well, and in fact one of the more common is literal line of sight. Can you see point A from point B? Two different functions in the application. We'll take a look at those two analysis functions. I think one of my favorite terrain modeling tools is Watershed. There are, again, multiple themes that we can look at. We're going to highlight a couple of specific ones where we'll analyze the ability of the terrain to support the flow of water, and the byproducts we get from that are things like flow determination or water drop analysis, as well as determination of catchment area, perhaps for protecting a water supply. And we'll look at those two scenarios. These are all, by the way, derived from terrain. Obviously, the underlying basis for all of these analysis tools is the presence of a terrain model. So while we model watershed delineation, this is not necessarily a determination of where water actually is present, but we'll address that when we get to that section. Slope analysis, there is a visualization that can be applied to any terrain layer to determine not the elevation at a given point, but the angle or indeed the bearing of a slope. And we can take that information and do a little more analysis. I'm going to introduce a very interesting visualization based on our quiver plot generation functionality, where you can visualize the slope characteristics at defined locations, and maybe again to determine the optimal location for an engineering project or a construction project. But being able to determine that visually on the map, very, very simple but very powerful function. One of the conversations we're engaged with quite a lot is this idea of change detection. With the readily and expanding availability of terrain data, perhaps a temporal series where terrain information is captured at a certain time frame and again at a future point, there's obviously the ability to determine the level of change that has happened between those two periods. And we'll take a look at one very specific example at a very micro level. This is a very localized surface model that I will show you, and we're going to detect what has changed within the time frame from one of the data collection paths and the next. So very interesting application that I'll show you later in our session. So the first bullet, as you can see, is terrain creation. Before we embark on any of the analysis functions, we're going to quickly take a look at how terrain is generated, the function for essentially taking source data, very often in vector format, more often than not in vector format, and generating a surface model from that. This could be LiDAR data. We'll take a quick look at some point cloud data, do a little bit of filtering to generate some a terrain surface. We'll also take a look at a very simple XYZ file. And we'll also, while we're doing this, take a look at some of the online sources of data that are available for download, pre-created terrain data, in other words. So before we begin by addressing the process of creating terrain, very quickly, I'm going to take a look at the online data option here. Third button in from the left in my toolbar, you'll see where my cursor is located, a little globe right here. This is our access point for our online services. The same function, by the way, can be initiated right here from the introductory screen, download free maps imagery. We'll go ahead and select that, and you'll notice in the resulting dialog box we have a terrain section that allows us to access pre-existing, pre-created raster terrain data. Now here in the US we have access to the 10-meter resolution national elevation data set, very good for wide area applications, perhaps county-wide or widest or larger. Large surface area, obviously we're not dealing with something in a local context when you have a resolution of this size, but still it's readily available, free of charge, downloadable, can be rendered in real time, streamed from the USGS National Elevation Data Set. Globally, we also have access to a couple of options, one being the ASTER GDEM, Global Digital Elevation Model, which is a 1 arc-second resolution data set. Again, you can access this in real time and render it right on your screen. So those are a couple of options that are available at pre-configured elevation data sets you can access at no cost. You'll notice a few others in here. You will encounter occasionally some premium content. This is a subscription-based service, so if you wanted to access data from MapMart, for instance, you would need to have the appropriate subscription account with them. You would be prompted to enter that information while you are trying to access that data. So while we are going to talk about creating terrain in this section, it is worthwhile acknowledging that there is a lot of terrain already available out there. These are just some pre-configured options, and certainly in your context at a local level, you may have access to other services. You can add your own web map services here as well. With that, let's take a look at our first scenario, our first file. I'm just going to drag a pre-opened text file from off screen so we can take a look at our source data. This is a very simple file. We've got a numeric value with a comma, second numeric value, another comma, and then a third numeric value. Now, this first value is our X value. Second value is our Y value, and our third value in this case is our Z or Z value, or elevation value. So for that point, this is the elevation, and you'll see that's repeated throughout this file. That third value, by the way, while we commonly assume this is going to be an elevation, can be any quantifiable or numeric or measurable value. So you can use the same modeling process that I'm about to show you in many different contexts to visualize distribution of data. You can use the same visualization tools that we will be looking at for terrain in any different any application where you have a number assigned to a location. Now, noting the format, we have an X value, Y value, comma delimited, no header information, because we're going to be prompted in just a second to enter those parameters during the import process. I'm going to close the file, and off screen again, I'm going to quickly drag the file that we were just looking at onto my map. We could go to the file menu and initiate the import from there, but dragging and dropping is often the most straightforward way. Now, in this dialog box, we're being prompted to apply the parameters of that file. We do have a few options in here that allow us to immediately create an elevation grid from this data. I typically don't recommend that approach because I often find it valuable to see what the point distribution is like before actually rendering that. So we're going to bypass that. Although it is an option, we're going to simply display the points on the map. From there, we can manually go through the process for creating a surface. Confirming what we previewed in the file, the coordinate order. My easting is the first value. It could be X easting or longitude being that first value. So we'll leave that setting as is. Coordinate format, decimal or separated is fine. We'll just leave the default. This value of 0 confirms that there are no fields to skip at the start of the line, nor are there any rows that we need to skip either. So there's no header information, there's no additional information. Everything here again is as it should be. It is a comma delimited file, so we can make sure we confirm that setting. We're not concerned about our classification or feature classification. In other words, the actual feature type that's going to be assigned to these points. These points are just a means to an end rather than an end in of themselves, so we can just leave this as a default. That's fine. There is no additional attribution. Although we have that third coordinate value, we don't need to worry about that in this case because there is a dedicated setting that treats that third coordinate value as elevation, and that's exactly what we want to check here. So with those settings applied, we will see an array of points displayed on our screen. The final setting, by the way, when I click OK, is to confirm the projection parameters. Now, in this case, it has remembered the settings that I applied previously. So this is a UTM projection that was the XY values, and the zone is zone 19 here in the Northeast US. So everything here is fine as well. We'll just confirm and click OK. And very quickly you can see now we have an array of points on our screen. These points, obviously very regularly spaced points, or artificially created. They don't represent a typical source data set of this type like LiDAR, where it's more randomly distributed, but it does give us the basis for visualizing a process for converting simple point data into a surface. Now, to confirm, when I select an individual point, you'll note the elevation value is present right there. So each one of these points has a known Z or Z value. Okay, so now we have the raw material in place, and this is the critical step. How do we convert this into a surface? How do we generate a terrain model from an array of points? Well, obviously, the process is going to involve some level of interpolation because these points are fairly widely spaced. These are 10 meters apart, I believe, and as such, what happens in between, Global Mapper is going to have to interpolate or guess. So the resolution of the resulting file will reflect that spacing. That conversion process is initiated in the analysis menu. And you'll see here, very first option is create elevation grid from 3D vector data, which in my case is my 3D points. We're going to encounter this dialog box again in a few minutes, but for now, all we want to do is simply generate a very simple elevation grid. It is going to be a raster layer. We have the option of naming it appropriately. Default here is elevation grid 1. The vertical units we can confirm are meters. That's fine. Everything else should be okay here. We are going to retain the automatic determination of grid spacing. In other words, we do not need to define the resolution. That's going to be derived from what Global Mapper sees in the distribution of the points themselves. So everything here is fine. I simply click OK, and my surface model is automatically generated. Now, because of my layer order, my overlay control center, it has overridden the points, which is fine. They are sitting behind the model here, but you can see now a raster surface model has been generated, and to verify, I'm going to simply open my 3D window, and you can see this is actually a 3D model. A 3D rendering of the terrain, again interpolated between those 10-meter spacings. So that's the very simple process of generating or creating a terrain layer from some source data, which in this case is very simple X, Y, and Z files. In this next example, we're going to basically follow the same process we saw with our simple XYZ file, except in this case it's going to be based on a point cloud, a LiDAR point cloud, but we're going to go through the procedure for transforming a LiDAR file into a surface that we can then ultimately use for whatever terrain analysis we need. Again, from off screen, I'm going to quickly drag a sample of some LiDAR data, drop it on my map to initiate the import process. In this case, this is a very specialized file. You'll see some of the options in here are very unique to LiDAR data. Both LAZ, LAZ, and LAS are supported. So regardless of the format of your LiDAR data, you're going to encounter the settings you see here, the options to apply the settings. Now, I typically recommend that you bypass this window, and if you need to initiate a filtering process or any sort of paring down of your point cloud, you do that after the file is imported. So in this case, I'm simply going to bypass the options, simply click OK, and it should ultimately render the point cloud right on my map. Now, one of the things you will see, I'm going to drag my overlay control center in from off screen so we can note the metadata tab here. One of the things that I would need to determine before I generate a ground surface model, a DTM, is whether or not my point cloud is ground, or whether it's unclassified, or whether it's a combination of different types. Obviously, I don't want to assume that every point in this point cloud represents the actual ground level, so I may need to analyze that to determine which level of filtering I need to apply. Now, in the metadata for this point cloud, you'll notice a statistics tab, which includes a breakdown of all of the classification codes. And you'll note here that most of the points in this case are actually unclassified. I've only got a very small percentage, I think 13 million is the full point count. Only 3 million or 3.5 million of those are actually ground. Now, in this example, the reason for that is because this is a heavily vegetated area. So I think most of these unclassified are likely to be trees, multiple returns perhaps from laser pulses that have actually encountered leaves and penetrated and given us more than one return per pulse. But we do have, again, a number of ground points that we're going to use in this case for generating our surface. We'll go ahead and close the metadata and initiate a filtering process. Now, I don't have the LiDAR module active here. If you do need some more advanced LiDAR processing functionality and you haven't looked at the LiDAR module, you may want to take a look at that, because it does give you a lot more capability in terms of processing LiDAR. But you can, at the very least, perform at least a certain level of filtering, which I'm going to initiate from the configuration dialog box. You'll see the LiDAR tab here. Right now, all of those classifications are now enabled, and I'm going to disable all and simply turn on those that are deemed to be ground points. We'll click OK, and you will see behind now we've got a slightly less dense point cloud. You'll see it's quite clear now that there's gaps in the data. If I zoom in a little closer here, it might be a little easier to see. You can see definitely there's a lot of spaces in here. This, again, as I mentioned before, is a fairly forested area, so you're looking at a relatively lower point density than you would find if it was open area. But for our purposes today, the idea of using this as the basis for terrain generation, same process as we initiated before. From the analysis menu, once again, we're creating elevation grid from 3D vector data. You'll see exactly the same dialog box we saw when we had our text file. There are a couple of additional options here that pertain to specifically to LiDAR, but without the presence of the LiDAR module, you will not actually be able to use these. These include binning and triangulation. Triangulation is the default, but you can also generate a surface model based on the binning process, which is essentially an averaging process. We're just going to go with the tinning procedure. One of the other things you'll see here, which may be useful in certain situations, is what to do when there's no data. Now, in this point cloud, you'll notice that there are some fairly large gaps. If we leave this slider all the way over to the loose side, what happens is that Global Mapper will essentially bridge those gaps and create an interpolated model to fill in where there's no data. The further you slide this over towards the tight area, the tight side I should say, you will find that Global Mapper will actually leave those gaps and there will be no terrain surface. There'll be a null area. So really, depending on the application, you can choose either to leave this loose or move it towards the tight side if necessary. I'm going to leave it right there. I'm going to limit the extent of my terrain generation to a relatively small area. just in the interest of time. So again, under grid bounds, I just simply drew a box. All of the settings should be fine. We'll click OK. And once again, we see our small section of terrain data. We took our source data, which is our LiDAR point cloud, performed a very simple filtering process. We know all the remaining points are recognized as ground, and as you see, we generated a terrain surface as the basis for some of the analysis functions that we're about to show you. So in this next section, we're going to take a look at a couple of variations on the theme of calculating volumes. Obviously, the process of having terrain data, modeled 3D data, gives us the opportunity to calculate capacity or volume. And there are multiple tools in Global Mapper that you can use within this context. I'm going to show you a couple of very simple ones to begin with. Measuring volume simply by defining an area that encompasses the pile that you want to measure, perhaps, or the capacity of a depression. We're also going to look at having two existing surface models and being able to calculate the volume that lies between those two areas. So here we have a small section with some pre-configured terrain data. This is again LiDAR derived, very small area. Very noticeable here in the lower left corner is what appears to be a pile of material. I'm not exactly sure what it is. We're going to take a look at this and determine what the capacity or the volume of this pile is. Also, and the reason I chose this example, I use this one quite a lot, is on the upper right corner you'll notice quite a distinct depression. This actually happens to be a disused quarry. And we're going to go through a couple of scenarios where we're going to first of all determine the volume of this pile, and then using the same procedure, the capacity or the volume that was likely removed to create this quarry. So in this situation, I've actually got a couple of things pre-configured. The determination of the volume is based simply on the creation of a polygon or an area feature, which is what I've already done here. I simply drew the outline. Now, it doesn't matter how precise this is. I didn't have to make sure that my polygon was right at the transition from the flat surface to the pile. That's not necessary because it will base the calculation on the volume it sees within the extent of the polygon. Another item of note, and I think the best way to visualize this is if I use my profile tool, is that this pile is not on a flat surface. You'll note here that the upper side of the pile is actually on an elevated surface, and further down obviously it's a little lower. So the determination of volume is going to have to be based on what it sees as the original surface. In order to determine that, as part of this procedure, Global Mapper will sample along the bounds of this polygon the elevation values and create a temporary surface model that will allow me then to calculate what's above that model. Now, we don't see this happening. There's no dialog box that prompts us to create that model. It happens as part of the calculation process. The action that I need to perform is simply the selection of the pile outline and a simple right-click process to get to our analysis measurement function, and we have a pile volume option right here. Calculate the volume of the selected pile. Once again, the determination of the area is simply an arbitrarily drawn polygon in this case. Now, if I select that option, very quickly you'll see Global Mapper has performed that calculation for me. I've got the total volume in cubic meters in this case, the net volume, cut volume, and the fill volume. Now you'll notice the fill volume is a relatively low value. That would represent areas within the extent of my polygon that are actually below rather than above the interpolated terrain. So there is a little bit of data that actually dips in here, probably something, some areas right along the edge of the boundary. It actually is a little depression before it actually rises. But the calculation of the net volume, as you'll see here, factors in those fill areas. Now, the summary, as you'll see at the bottom, we can then copy that to our clipboard, export it to a CSV file if needed. So very quick and easy way to calculate our volumes. We'll close that dialog box, and indeed we will deselect and close the pile outline and perform exactly the same procedure, but in this case it's a polygon that encompasses the extent of what I said previously is a depression in the terrain. So again, using my digitizer, just simply select the boundary. Again, there's no inherent terrain characteristics associated with this polygon, simply arbitrarily drawn with the digitizer. I will then right click again go to my analysis measurement options. Once again, pile volume, a little bit of a misnomer perhaps because it's not a pile in this case, it is a depression. But as you'll see, where previously it gave me a fill volume, in this case, it will focus on the cut volume. I'm sorry, other way around. It will focus on the cut volume as a negative value. You'll notice my net volume is now negative. My cut volume is, again, relatively low. This implies it's a depression. We have a net volume, as indicated in our summary, of just under 10,000 cubic meters. So that would represent perhaps the amount of material that was originally extracted to create this quarry that I mentioned previously. So those are just a couple of variations on a very simple process for calculating volumes simply by defining the geographic extent and having Global Mapper do the computation. The next volumetric calculation workflow essentially does the same thing that we just demonstrated, but it does it in a much more manual way, because rather than having Global Mapper manually determine the base level from which to calculate volume, we actually have that data in place already. And to prove that, I'm going to use my image swipe tool. I'm going to pull back this surface model, and you should see underneath we have what essentially is a subsurface layer. You'll notice the shading values indicating that this is much lower than the surface layer. So what I want to do is I want to measure the volume between those surfaces, and I can do this for the entire area, or I can do it for a smaller area if I have a polygon, for instance, defining the extent of what I want to analyze. But the ultimate result will be the same, and the process for calculating will be the same as what we saw with our pile volume calculation before. In this case, the procedure is initiated right from the analysis in Global Mapper. There are actually a couple of variations on this theme. One is our compare combined terrain layers, which ultimately allows us to model the difference between those two surfaces. The other one is to perform the calculation, which is measuring the volume, as you can see, measuring the volume between surfaces. Very simple dialog box, choosing one of the layers. Doesn't matter in this case which one we choose to subtract from and subtract to. The values are what's most important. We have our volume units can be defined here as well, and just in the interest of time I'm going to define the bounds. Once again, if I had selected a polygon, I could simply measure that volume within the extent of a selected polygon. In this case, I'll just simply draw a small box. It's only going to measure the difference within the extent of that box. Click OK and click OK, and the result of this process is a series of numeric values, as you can see. The total volume between my surfaces, as you can see here, is just over 4 million cubic meters. So that subsurface layer, that ground layer, for the extent that I defined, that is the capacity or the volume. If this perhaps was a quarry, a potential quarry or mining situation, or some sort of extraction process, you can very quickly calculate and determine the amount of material that's within that area. Next on the list, as you can see, is terrain flattening. This probably belongs in the previous section, but I decided to make it its own bullet because it's a very, very powerful tool. It is a volume calculation tool. We will ultimately generate volumetric measurements, but as a byproduct, we will also generate a surface. We can define initially the geographic extent, just simply based on a polygon, as you will see, and determine the basis of our flattening. You'll see in just a few minutes there are various options for determining how to flatten the terrain, what parameters we will use. But as I said, the ultimate goal is the calculation of volumes required for that flattening process, and ultimately a modified surface that will actually show that flattened area. So what we have on the screen is our terrain surface. This is the same LiDAR derived surface that we were working with previously, and a rectangular feature. Now the rectangle itself doesn't have any inherent characteristics. It's simply a boundary, if you like. Perhaps this represents the extent of a construction project or some sort of engineering project, and in real terms I think my choice of location probably isn't the best, because I placed this, as you will see when I open up my 3D viewer, on perhaps the steepest part of the slope. But I use this for effect. This is obviously very hypothetical. My objective in this scenario is to determine the best practice as far as engineering is concerned that will allow me to create a flat surface represented by the extent of this polygon. And as I said, there's several ways that we can initiate this. The process is initiated with the selection of the area. I'm just using my digitizer. You select the area, and then it's a right-click option under Advanced Feature Creation Options where I can create a flattened site plan grid from selected area. In other words, I want to flatten the terrain and ultimately generate a surface model based on this area. Now, the dialog box that you see is actually fairly straightforward. What happens under the hood, so to speak, is very, very powerful. You will notice the first selection I'm prompted to choose here is what to base the flattening on. Perhaps the most straightforward way is simply to define a height. So while there is no inherent height applied to this rectangle, I can manually assign that right now. I can tell Global Mapper, let's flatten it to a height of 100 meters, in which case it will determine the amount of material that will need to be cut and or filled to create that flattened surface model based on that extent. That again is a manual input process. Moving to the third option, I could apply the elevation that's inherently in the polygon itself. Now, as I mentioned, there is no elevation value associated with this polygon, but if there was, I could simply tell Global Mapper to look at those values or that value and flatten the terrain accordingly. Now, when I said those values, you can actually have a different elevation associated with every vertex. So if I wanted to create a flattened surface which was slightly higher upslope and slightly lower downslope, that would allow me to do that by, again, applying the per vertex elevations to this flattening process. Not going to do either of those two in this situation. Rather, what I'm going to do is have Global Mapper do the work for me, because we're going to have Global Mapper determine the optimal height that would require the least amount of engineering. In other words, while we cut from one side and fill on the other, we want to avoid a situation where we have to physically remove material or bring in material to ultimately generate that flat surface. So we're going to create ultimately a break-even height that we can provide to our engineers or our contractors and tell them that is the basis of the flattening. Now, over and above simply flattening the terrain, we can also factor in slopes. Based on a slope value, you'll see here we've got a 0.3 slope, which equates with a 1 in 3 or close to 1 in 3 slope. A 0.5 would be a 1 in 2 slopes, and you can see how that pattern continues. This will also be factored into the equilibrium as far as the volumes are concerned. How much do we need to cut to create those slopes, or how much do we need to fill to create those slopes, upslope and down slope, so they integrate within the existing terrain. We also have the option of terracing or creating benches around the edge if that's how we want to integrate our flattened surface into the terrain. With these settings applied, I'm just going to simply click OK, and we're going to see initially that it will go through several different possible optimal heights, showing me the calculations. Ultimately, when this finishes, it will have calculated the best possible break-even height. And you'll see that report now generated here, where my cut volume, 477,000, is close, not exactly the same, but close to my fill volume. By the way, the reason they're not exactly the same is quite simply based on the resolution of the data. But that's fairly close. That gives me an idea as to what my cut and fill volumes will be if my break-even height is 102.44 meters. So we know exactly what the break-even elevation will be of our flat surface, and that is calculated based on the equilibrium of our cut and fill volumes. So this information, as you can see, is copied to my clipboard. I could paste it again into a report or a proposal that we submit to my contractor. But when we're done, we click OK. And we then see the results of that process as a surface model. We can now see a modified surface model right on the screen. And the best way to visualize this is to open up our 3D view, and you'll see, again, this is an exaggerated view, by the way. I have exaggerated the terrain, but you'll see that flat surface, which is again around 102 meters, I believe, integrated into the surrounding terrain, essentially replacing the surrounding terrain where our cut volumes and our fill volumes have been equalized. And if we need, we can export this surface model, and it will integrate both the original ground and this modified area into a single elevation layer. So one of the more common uses of terrain data, one of the more common outcomes or the procedures that's followed is the generation of contours. A very, very straightforward process, very powerful tool. Many users of Global Mapper, as I mentioned, focus on this or cite this as being one of the strengths of the application. We started with vector data as the raw material for generating our terrain. Now we're going to go back to vector data in its contour form, so we're kind of transitioning back into generating vectors again. In this case, we're looking at a relatively low resolution elevation model. This is a layer that was derived from the 10-meter resolution national elevation data set that I showed previously when we looked at our online data sources. And we're going to generate some contours just for our screen area. We're going to show you how that process works. Again, from the analysis menu, we initiate the process of generating contours from right here, generate contours from our terrain grid. You'll notice an option as well to generate contours from tin. That would be a vector triangulated irregular network layer that can be used as the basis for generating contours. We don't have a tin on our screen, so we're going to go with the option to generate from our terrain grid. And the dialog box, as you'll see, allows us to establish the parameters of these contours. Ultimately, we are generating a vector layer, so we can assign it a name. I would suggest you name the layer based on whatever the contour interval that you've defined. Mine is preset to 5 meters. This is, again, the vertical distance between adjacent contour lines. We'll leave that as 5, but make sure that you label it accordingly. I always find it a good idea. So I'll just call this 5-meter contours. Now, we could generate multiple different contour layers, a 5-meter contour, maybe a 1-meter contour if we're looking a little closer. But we'll leave these as is. We'll generate our 5-meter contours. The option here, which I'm not going to use in this context but gives you flexibility for certain other applications, is to generate a contour that's only at a certain height or a specified height. Rather than generating contours every 5 meters, we can define a very specific elevation here, and with this checkbox checked, it will generate just a single contour representing that elevation. We'll leave that unchecked in this situation. The contour interval multiplier are basically settings that allow you to determine the boldness of the contours. Every 4th contour will be a bold, or very often referred to as an index contour. Every 8th will be even bolder. That's what those settings apply to. The elevation range is defined. We'll leave that as is the resolution of the data. And one other thing to point out right here is to generate an area or areas rather than lines, or I should say as well as lines. So you may want to use this option if you want to simply determine the extent of the area that's above a defined elevation when used in combination with this dialog box at the top. So for instance, if I typed in 100 meters, check this box, and check this box, ultimately I would get a series of polygons that enclose everything in this area that's above 100 meters. Now again, slightly more creative use of our contouring function. We'll again disable those for this application. The final box I want to show you is the option to generate spot elevations. There are multiple ways of determining the maximum and minimum elevation within an area. This option, I think, is the most straightforward. It'll simply put a point right where it sees the highest point and ultimately the lowest point. I think most people are probably more concerned with the maximum elevation, but you get the minimum as well, and we'll see that in just a second. Everything else here we'll leave as is. The only thing I want to specify is the geographic extent, and in this case I'm just going to draw contours for what's currently on my screen. I could, if the workflow prescribed, I could define the extent of the contours based on a selected polygon. That would be an option at the bottom, but we'll just again base our contour generation on what's on my screen. Click OK, and you'll see the results of that almost immediately. In this case, I'll turn off my underlying elevation layer, and you'll see my contours have been generated very quickly, very easily. Somewhere in here there should be a couple of spot heights. I can see the max elevation right here, this little green triangle. Not quite sure where the min is. I think it's off the side of my screen over here on the right side. But again, most people would be concerned with determining the high point. Perhaps if you're initiating a Viewshed analysis, you want to determine the high point within an area. That's a useful byproduct for that process. But what we have here are ultimately vector lines. As with any vector line, we can edit them if necessary. You can see I've just selected a single line here. You can initiate the digitizer to do a smoothing process perhaps. remove some vertices manually if that's applicable. You can redefine the visual appearance. They are obviously inheriting a default appearance. These brown shades are defaulted within Global Mapper. So multiple options as far as in editing those vectors are concerned. And ultimately, for many users, exporting these is the next step. I need to get these into my CAD system, or I need to get them into my other GIS software. Very simple process to export these linear features now in any of the supported vector forms. But again, raw material in this case was our terrain grid. Global Mapper analyzed the terrain and ultimately generated our linear features, our contour lines. Very, very simple process. In this next section, we're going to take a look at a couple of variations on the idea of analyzing visibility. One is based on a straight line. Can I see point A from point B to two defined locations? And the other is from a defined location, what can I see looking in multiple directions? That's my Viewshed analysis. So I get variations on this theme. As I mentioned during the introduction, these are often applied for broadcast applications, and you'll see many of the parameters are specific to that technology, but it can simply be used for literal visibility as well. If I'm standing on the mountaintop, what can I see? So once again, we're going to run this analysis on this lower resolution elevation model, this 10-meter DEM. You'll notice I have a line feature already created here. The line of sight analysis obviously is dependent on the existence of a linear path, starting point to finishing point essentially. You can initiate that process from the tool itself. Right here in the toolbar, I'm selecting the path profile tool, and my line of sight analysis can be derived simply from arbitrarily drawing a line on the map. Now, in most situations, I would not suggest taking that approach because obviously you're arbitrarily selecting a point of origin and a destination point. It's much more likely and certainly potentially much more accurate for you to perform that analysis based on a linear path that you have already defined. Perhaps it's something you've imported or based on known coordinates where you're analyzing. So in that context, what I have on the map now is a line. It's simply a two-vertex line, and I'm going to define the line of sight from the starting point, which is here in the bottom of my map, to a defined destination point. While I could, as I said, initiate that with the path profile tool, what I'm going to do instead is simply select that line with my digitizer. I'm going to right click, and all the way towards the bottom of this right click menu, I'm going to choose analysis measurement, and you'll notice in here the very first option is path profile. This is going to initially generate a floating window showing me a much exaggerated perspective of the terrain under that line feature. Now I say much exaggerated. You will notice that the horizontal scale goes up to almost 6 kilometers, where my vertical scale ranges from 50 meters to 120, so about 70 meters of vertical scale. So you can see it's really not as exaggerated as it implies. But in many situations it is useful and worthwhile to have this exaggerated to fully accentuate the extent of the dips and the valleys and the ridges, etc. in your terrain. This is a floating window. By default, as you can see, I look behind, I can see the line, and if you're working with multiple monitors, you can certainly use this second window, drag it off to a second screen. Obviously we don't have that luxury when we're doing this presentation, so what I'm going to do instead is initiate the docking process that we have available in Global Mapper 17 with the introduction of Global Mapper 17. If I select this option right here in the toolbar, I now have the choice to put this profile view right along the bottom of my map screen. I'm going to do that right now. Click OK, and you'll see it now occupies a docked view as opposed to a floating window view. So again, that was initiated right here with this button. I can undock it as well by once again clicking this little button that you see right in the dialog box. But this is a good perspective because it shows me as I move along my path where I am in the corresponding top-down two-dimensional map view. I'm just moving back and forward. So the path profile display is a cutaway cross-sectional view and is the basis for our line of sight analysis. Right here in the toolbar is the button that allows me to calculate that line of sight. If I select that, I can enter the parameters. The significant ones here and the important ones are to determine more precisely the from and to site elevation based on the your height above ground. If we leave these at 0, if we leave these in the default state, and I have previously edited the values, that's why it's retained them, but if these were left at 0, the analysis would be conducted quite literally if you were on the ground looking in a particular direction. We want to exaggerate these a little bit. Now for effect, I'm going to assume that my from site elevation is about 10 meters. That would assume perhaps I'm on a lookout tower, or if it's a broadcast application, my transmission tower is 10 meters tall. So we'll leave that as is. My to site elevation, in other words, what am I looking at from my starting point, we'll assume that, again, we're not interested in the actual ground, but an object that perhaps is 2 meters above the ground, maybe a rounded off height of a typical human being. We'll leave that as 2 meters for that purpose. Now, we're not interested in our Fresnel zone specification, because in this context, we're not dealing with a broadcast application. Everything else should be fine, and if we click OK, we should now see in our profile view, first of all, the artificially exaggerated elevation at my start point, which is again 10 meters above ground, and you'll see the straight line path to my destination, which is my 2 meter exaggerated elevation at my end point, and you will see quite clearly that there's an obstruction in the way. So in this very simple analysis, we can see that if we were hoping to see point A from point B or vice versa, we would have to do a little engineering perhaps to remove the obstruction, or in this case maybe a taller lookout tower will be required, or move the destination will be another option. But you can see this analysis gives you that information, single line linear visibility. The Viewshed analysis process takes a slightly different approach, because when we're dealing with visibility along a single path or a single line, it's obviously very easy to define that path. With Viewshed analysis, what we're analyzing is visibility in multiple directions from a defined point of origin. And what I have on the screen is a single spot height that I created, defined by the highest point in this area. Ultimately, I used the same contouring function that we introduced a few minutes ago to determine the high point of land here. And I'm going to analyze in all directions what coverage I have, in other words, what's visible and what's invisible. And we're going to use the same parameters that we had for our line of sight, a 10 meter artificially exaggerated height, looking at a 2 meter person, I guess. At some point, what coverage do we have? What areas would we not see that person within the extent of our analysis area? For this analysis, I'm going to simply use the digitizer to select that source point. I'm going to click the button in the toolbar to generate a viewshed. Now, as with the line of sight, I could simply select that point of origin manually, but because I have a digitized point already selected, simply clicking somewhere on the map will give me the option to create the viewshed for that point, as opposed to the clicked location, yes and no being the options here. I'm going to click yes in this case, so my analysis will be derived from this predetermined location, and many of the settings you'll see that can be applied here are the same as those that we saw with the viewshed analysis. The transmitter elevation and receiver elevation, again predetermined here because I had set them before. The idea of Fresnel zone specifications, as well as free space path loss, derived from the broadcast application. Unlike with the line of sight, in which the linear path was defined, there's a few additional settings that I need to apply here. First of all is the angular extent of the analysis. We first of all define a start angle, that being 0, being true north, and from that start angle define the sweeping angle. How much of a range from that starting point are we going to analyze? Well, in our case, we want a 360-degree perspective, so we can leave these values as they are. In other words, starting from due north, we're going to analyze in a full 360-degree arc. So we'll leave that as is. The other thing we need to determine is the extent from the point of origin that we're going to analyze. This is set to 5 kilometers, and I'll leave that as is. So in other words, it's going to analyze out to that point. You will also notice I have the option of defining a minimum radius. If we're not concerned about analyzing visibility within the first kilometer, for instance, or cell phone coverage or radio transmission coverage within the first kilometer, we can define a minimum value as well. We're not going to worry about that in this case, but those are options. We'll just simply click OK with these parameters established, and this process actually generates a new layer for us right in Global Mapper. So it's analyzing the terrain, it's analyzing the degree of visibility, and it will show us with an area feature, or polygon, that we can ultimately export, our coverage area. And one of the options that I did not show you, perhaps it would have been more useful in this context, is not to map what I can see, which is what I have here. I basically have the red areas indicating what is quite literally visible from this point, what can be seen. If I was hoping to hide, I could certainly occupy some location in here, and I could not be seen from the top of that 10-meter tower that we've defined. So red equals covered area. The area that's not shaded represents areas that have no coverage, that are in shadow. And an option in the dialog box would have been to delineate those areas instead of the coverage areas, which in many situations would be a more meaningful and a more useful outcome, is to show those areas where we don't have coverage. So again, Viewshed analysis, analyzing visibility, quite literally in this case, visibility from a defined height above ground, from a defined location, radiating out to whatever angle you want, to whatever distance you want, and ultimately generating our polygons that we can, if we need, export to any vector format. Next item on the to-do list is to take a look at watershed modeling. The idea of modeling or delineating the flow of water, essentially drainage patterns in the terrain, and it is simply based on terrain, accumulation, downslope. What's the likelihood that water will be supported by the terrain? I should stress as well, as I did at the start, this is not a analysis of the presence of water, because there are so many other variables at play, soils, geology, rainfall, etc., etc. That's not what's factored into this type of modeling. This is simply a terrain analysis function. And as I said at the start, we're going to perform two separate analyses to illustrate this procedure. One is a water drop analysis. We're going to define a point of origin and delineate where a water droplet would flow from that point. And we're also going to generate a catchment area that accumulates flow that ultimately ends up at a particular location. So for the first analysis, I've already defined the point of origin. You can see quite clearly labeled here, flow from point. We're going to analyze outflow from this very defined location. Quite literally, it could be used for drainage analysis. If we had a drop of water placed on the terrain at this point, all things being equal, where would it flow to? It's very common as well to use this as an analysis for perhaps outflow, not of water, but for some other commodity. If it's a pipeline that has ruptured, where will that commodity flow to? So this type of analysis is very useful for determining what protection needs to be in place downstream in the event of some sort of catastrophic rupture or something of that type. The process I'm going to initiate requires me to select that point as the point of origin, and then from the analysis menu, I'm going to choose the Generate Watershed option. In this dialog box, we can perform multiple types of analysis. One of the things that's very common is for the analysis to actually generate areas showing each individual drainage system. That drainage system is defined by an area threshold that we can establish either based on a cell count or based on an actual unit of area. We're not going to worry about that in this context, but you can define those polygons, those localized drainage areas, if that's part of your workflow. You'll notice a couple of checkboxes that are checked here by default, given that I'd selected a point. The one that we're going to use in this case is the flow from analysis. We're going to uncheck the flow to option and readdress that in the next scenario. This is all we really need to establish in this case. We're creating a new layer so we can name it accordingly. We'll click OK. Actually, I'm going to limit the extent before I do that. We don't obviously need to analyze the full extent of all of the data, so we'll limit the analysis to just what's on my screen. I know the actual flow model is going to be well within the bounds of the screen, but this will eliminate the need for Global Mapper even to address any data that's outside of the bounds of my screen. We click OK. And when the process completes, we will see a couple of things. We'll first of all see linear features defining where Global Mapper has determined that water is likely to flow, and a dashed line, a very clear dashed line from my flow from point indicating the outflow of that hypothetical drop of water to its eventual destination, which is right here at sea level. So that indicates the likely passage of whatever that commodity is through the terrain. This is again a fairly low resolution terrain model. This is a 10-meter resolution model. If you had a higher resolution model, you can be very precise in terms of the likely path of that drop of water. Now, this type of analysis is very useful not only in this context where it's a relatively hilly area, but in areas that are relatively flat where it's not as apparent where the flow patterns are. This gives you a very clear indication where that water drop would flow to. For this next example, once again, I've predefined a point of origin, a flow to point in this case, and we're going to analyze the full extent of the catchment area that ultimately drains to that location. An example of when this tool might be useful is in situations perhaps where you have a drinking water supply. Maybe this is where water is extracted for human consumption, so there needs to be some sort of regulation or limitation on what sort of development takes place upstream of that location. So what we're going to do in this scenario is delineate the extent of that area. Once again, selecting the point with my digitizer prior to going to the analysis menu, and once again generating Watershed. It has remembered what I had defined previously. All the parameters are here, including the description of the layer. I'm just going to call this layer Watershed, more appropriate in this case. We're defining the full extent. By the way, Watershed used on this side of the Atlantic. Sometimes catchment area would be the alternative that would be used in other parts of the world. That's ultimately the same thing. Once again, defining the stream threshold is an option. What's the extent of each individual watershed area? We're not tracing the flow from in this case. We'll uncheck that option, and in this case we're going to generate a watershed showing drainage to that point. The other important setting in this context is our flow threshold. Now for this example, if I zoomed in close enough, that point is actually located right at the bottom, the lowest point along that valley, a small little section, that river channel. This threshold value allows me to establish a fuzziness, if you like, so that if that point is not quite at the middle of the valley, so let's say it's up the valley side slightly, it will actually analyze based on a factor of the data resolution, which in my case is 10 meters. So this value gives me a buffer of 40 meters around that point, upstream of which it will analyze. This ensures that the analysis is actually conducted within the drainage area that's the required target. So we'll leave that as is. Everything else again should be fine. We'll once again limit the analysis to what's currently on my screen, making sure that we've selected our drainage to this time rather than our drainage from, and we'll click OK. Once again, it's going to go through and analyze the terrain to determine the feasibility for water to flow, and as a byproduct of our setting, it will ultimately generate a polygon, a large polygon. Should have probably extended my analysis just a little bit off the bottom of my screen, but you can see it's delineated the extent of what ultimately will drain to this point. So if we were in the process of regulating human activity or any sort of development, we have a very clearly defined linear path, or polygon I should say, within which we need to apply that regulation. This is essentially a watershed, this boundary. On the left side of that boundary, drainage flows in this direction. On the right side, ultimately flows in this direction. This is essentially like a localized version of our continental divide here in the United States, where we shed water in one direction or other. And again, ultimately a polygon is the result. We can export that polygon if necessary into any of the supported vector formats for use in another application if that's required. It's quite common for folks who deal with terrain data or elevation data not to be as concerned with actual elevation values as they are with slope. And slope is a byproduct of being able to analyze elevation. The relationship of a cell within an elevation model to its neighbors allows you to determine the angle of the slope. And as you'll see, there's a couple of ways in Global Mapper we can use that. I'm going to, first of all, initially visualize the slope data, the slope characteristics using a pre-configured shader. But then we'll do a little bit more analysis based on specific locations where we can determine and visualize the slope parameters across a defined area. So up to this point, the visualization of the terrain data that we've been working with has been based on the Atlas shader. You'll see from this drop down where my cursor is located at the top of the screen, this is our default. There are options for changing the appearance of our terrain or our elevation data, but Atlas is the default. And an Atlas shader is essentially a range of colors from red, yellow, green, right through to blues that encompasses the full extent of the elevation data that's currently displayed on your screen. There is an option, by the way, to resample that as you zoom in close. So within the extent of a given layer, you may see that color range, but if you zoom in close, you may want to resample it and have the same colors applied to what's currently displayed within the extent of your map view. That's an option you can apply in the configuration, but that is the default view. There are alternatives, including, as you'll see, a couple that specifically pertain to slope. One is this slope direction shader, which gives you kind of a weird pattern that's sometimes hard to figure out. And one of the things I do often suggest is, if you're interested in visualizing slope direction, turn off everything that's not south. Maybe you're just interested in south slopes. You can make everything that's not a south slope a white color, so it accentuates those areas facing south, or north for that matter. If you're interested more in north facing slopes, turn your east, west, and south, turn those to white. That's again a configuration option can be applied, overriding the default settings. The other option here is the slope shader itself. You'll see when I select that, the visualization of the terrain changes from elevation to actual slope degree values as defined by this range of colors from, in this case, it's white to black. You can change the colors, by the way. That is again a configuration option if you need to change those. Or indeed, you can develop your own custom shader to define the colors you want and the angle ranges you want as well. Unlike with our elevation shader, what we're looking at now is a visualization of relative flatness. Areas that are in the white area, right here in the middle of my screen, probably the best example, is a flat area. It's possibly a body of water. I'm not sure exactly what's here, but that's a flat area. You'll see those regions which are darker in color have more steep slopes, and again reflected in my legend. There is an option in the Overlay Control Center to actually vectorize this. You can generate vector features. I'm not going to do that in this context, but that is certainly an option. But here's one very simple way of at least visually analyzing patterns of slopes within an area by simply activating the slope shader from the shader drop-down list in the toolbar. The other way that I'm going to visualize slopes is through the assignment of a quiver plot, or an arrow if you like, to points on my screen. Now the first thing I'm going to do to initiate this process is first of all to define the extent of the area that I'm going to analyze. I've already created a polygon or an area, a rectangle, within which I'm going to analyze. Now my intention here is to create a point at a fairly regular interval within the extent of this rectangle. There are a couple of ways I could generate points automatically in this area. One is to generate them randomly, completely randomly, simply by right-clicking, going to my advanced feature creation options, and creating randomly distributed points within that area. So that would, as the title of the function implies, create randomly distributed points. There's no pattern inherently in those point distributions. The alternative is to generate a regular array of points. And the way that we can do that is using the grid tool in Global Mapper. Now this might seem like a little bit of a stretch as far as this tool is concerned, but if you think about the function of a grid as being creating a regular array of polygons, as you will see, one of the options is to deselect the creation of areas or polygons and instead create points at the grid line intersections, which is exactly what I'm going to do. I'm actually going to generate an array of points based on the cell width or the distance that I defined here. I'm also going to constrain those to the extent of the rectangle. So I'm going to calculate the number of points that fill a rectangle. And in this case, because I've previously selected that polygon, I simply crop to the selected area. I'll click OK. And you'll notice now I can no longer determine the number of in this case it will be points, because that's going to be done for me based on the extent of the polygon, but rather I can determine the distance between each one. I want to type in a value of 50 meters, both for the cell width, or that width, and the height. Now again, this will allow me to generate a regular array of points that are 50 meters apart, both on the X and the Y axis. I believe that's all I need to do here. I'm not concerned about the naming sequence. We'll actually disable the names in just a few minutes, but that would be how we could define how these points are going to be labeled. It's more useful if you're actually generating the area tiles themselves. We'll just simply click OK. And as a result of that process, you'll see I now have an array of points. Off screen, I'm going to go to my overlay control center for this newly created layer. Go to the options, and I'm going to disable the labels. Just for this analysis, we don't need to see them. So there we have our point features. You'll see they're encompassed with red boxes. If I can close, you'll actually see them individually. But each of these point features represents a sampled location that's 50 meters from its neighbors, again, both on the X and Y axes. Now, the next thing I'm going to do, these are just arbitrary points at this stage. So the next thing I'm going to do is actually apply the elevation from the underlying terrain data to each of these points. So let me turn off the original area so we can remove that from the map display. The way that works, because they're already selected, I simply right-click on the map and go to the attribute style functions, and you will see an option here to apply elevations from terrain layers to these selected features. I have all of the points are now selected, so this is going to automatically add additional attributes to each of these points. Would I like to append the units? And I would say yes in this case. So I now have, for all 5,326 features, I now have the elevation values assigned to each point. Over and above elevation, if I use my feature info tool, you will also see that I have the slope and the slope direction derived from the position of that point on the terrain layer. And it's these two variables that I'm going to use to create an interesting visualization of slopes within this area. So knowing we have slope and slope direction. The way that this process works is through the creation of a quiver plot. And a quiver plot is an option, a visualization option for a point layer that can be applied in the overlay control center using the options. Under our point styles, you'll see the option all the way at the bottom to use a quiver plot for our direction vector variables. You can use the U and V components if they're present. If you're working with data that has a U and V component, just simply choose the appropriate attribute representing your U and V. Those are velocity along the X and Y axis respectively. But in this case, we have a direction and magnitude variable pre-configured. So we'll use that alternative. My direction is my slope direction, and my magnitude in this case is the slope, which reflects the slope angle. And when I choose that and click OK, and by the way, we can define the symbology as well. This is just going to be a generic black arrow assigned to each point. We click OK, and we click OK again, and we can see a very interesting visualization of our slopes. I'll turn off the underlying elevation to make it a little clearer. You can see some very interesting patterns in this area defining the slope variables. A little bit far out probably to get a good idea, but you'll see quite clearly. I'll turn the elevation actually on again, but I'll change it back to my atlas shader. That might give us a better representation of what's actually at each area. You'll notice a fairly high point of land right here, relatively high, from which the slopes are relatively steep, pointing out in either direction. Moving over here where we encountered a relatively flat area. I'm not sure where that was. I think up in this area. You can see very, very small arrows all pointing essentially in the same direction. So this is just a different way of visualizing slope, of being able to determine the slope patterns. In this case, it's by using our quiver plot function in Global Mapper. So for this final scenario, we're going to take a look at change detection, and the example we're going to use is at a very micro level. We have a couple of point clouds that were generated photogrammetrically. These are not the typical airborne LiDAR that we've been used to dealing with, but this is a couple of different data sets that were generated locally simply by analyzing photographs. And the change that we're going to try to detect between these two different data sets is the simple removal of a couple of pebbles from a pebble field. As part of the process, we're going to first generate a terrain model, a localized terrain model representing the two different pebble fields, and calculate the difference between the two so that it hopefully should give us a clear indication where those changes occurred. So here's the pebble fields as indicated, and you'll note if you look over on the left side of my screen the scale involved. This is obviously very localized. We're dealing with a meter, or about 3 feet being the extent of the area. And I've defined a boundary, by the way. This bounding box you can see here in black represents the extent of what I want to analyze. Just to show you this, by the way, this is a very interesting data set in 3D. You can see this is quite literally a local pebble field. And our challenge in this exercise is to determine between two separate layers which pebbles have been moved. I think there are 3 pebbles that have been moved or removed between the creation of one of these data sets and the other. So our objective in this exercise is to determine which pebbles have been removed. And we're going to do that again by performing a very simple change detection exercise. Now, to streamline this process, what I have done is actually generate, I'm going to turn off the point cloud, I've generated a couple of elevation grids. This is basically the same data that we saw previously, but in its gridded form. You can see this is now essentially a terrain layer, a localized, very localized terrain layer representing this pebble field. There's from the first pass, and this is from the second pass. So what I want to do is to determine the significant areas of difference, which hopefully will allow me to pinpoint exactly what has been removed between the first layer and the second layer. And that process is initiated from the analysis menu in which we perform the combine, compare terrain layers. Now, when people read this menu item, it sometimes gets a little confusing because they think the idea of combining layers is essentially a mosaicing tool, and that's really not what we're doing here. The compare and combine terrain layers allows you to perform an operation against 2 elevation layers. You can subtract, you can average them, all sorts of options as far as generating minimum, generating maximum between the two, multiplying the values together, etc. These are all functions that can be applied based on these 2 selected layers. In our case, what we want to do is simply subtract the 2. Now, the idea of either signed or unsigned really is not that relevant. All we want in this case is an actual difference value. So we're going to leave this unsigned. We're going to choose our first elevation grid and subtract our second elevation grid. That's really all we're going to do in this case. And as a result, we're going to generate what we refer to as a combined elevation grid, or we could probably more appropriately name this a subtracted elevation grid, or the difference between the 2 existing elevation grids. But we'll just leave that title as is, or that heading as is, and we'll simply click OK, and we'll allow this to run through, and for every pixel or every cell within this elevation layer, it's now subtracting the corresponding cell, or the value in the corresponding layer that's sitting on top. And as a result, when it completes, we should see a new layer in our overlay control center, and my fingers are crossed here, that should hopefully clearly highlight where those pebbles have been removed. So I'm going to turn off the other 2 layers so it'll remove the shader. I actually probably should define this as its own shader. Let's see if I remove that overlay, because we're finished with that. Remove the other one, and it still has not reset, but that's fine. I'll zoom in a little closer and perhaps that'll make it clear. But you can see very, very clearly here on my screen, that's a little clearer, 3 distinct areas where there's obviously a significant difference in the elevation. Now, there's some little anomalies you'll see scattered throughout the pebble field, but very clearly in the 3 areas indicated, there has been significant changes applied. And if I turn on, I'm just noting the location here, and I'll turn on the point cloud, and we should then see quite clearly where my cursor is located right now, where those pebbles have been removed. And we're able to detect that through this analysis of change. And this is a very localized scenario, but as I said in the introduction, if you have access to data based on a time series such as this, then it's very feasible that you can generate this temporal transitional model, if you like, to analyze those differences or those changes over time. So that brings us to the end of our webcast for today. Hopefully we gave you some ideas as to how Global Mapper can allow you to analyze the terrain. It's a very simple workflow, some a little more involved workflows as well. If you're not currently using Global Mapper and you want to try the software, you can download a copy. Go to our website, as indicated at the bottom of the screen. You'll see our address, our web address. Go to the Global Mapper section. You can download the software and try it out for 2 weeks. If you have any questions, as I indicated at the start, if you have any questions on any of the functionality I described today, or indeed anything that you encounter with Global Mapper, don't hesitate to contact us at geohelp@bluemarble.geo.com. If you want to interact with other users, I recommend visiting the forum and registering with the forum. You can certainly browse through some of the topics that have been posted there, or indeed post your own questions if you want help a peer-to-peer learning experience. So once again, thanks for joining me today, and I look forward to speaking with you again next month.